It is now my pleasure to introduce Dr. Neil Humphrey. Neil was a Canadian, is still a Canadian, but a few other citizenships. He came down the West Coast for his education, starting at the University of British Columbia in Vancouver, where he got his bachelor's, then his master's and PhD further south at the University of Washington. Continued even further south to Caltech for his postdoc. And since then, he moved east to the University of Wyoming, where he has taught for over 25 years in the Department of Geology and Geophysics. His interest of study has been snow and ice, focusing on the dynamics and hydrology of large ice masses. So he has worked in the places you would expect: Antarctica, Greenland, Alaska, the Himalayas, lots of, as he would describe, very wet, cold, miserable, but also stunning places some of the time. He has over 100 publications in major journals, and his current NSF-funded project is trying to figure out what's happening with Greenland and how much of that ice is going into the ocean and going to affect all of us. That requires him to spend a month up there on the ice sheet each summer. As an addition, he is also an adjunct professor in theater and dance, where he teaches vertical dance. We won't be getting a lot of that tonight. So please join me in welcoming Dr. Humphrey.
Thank you for that intro. So I've worked on glaciers for a long time, close to 50 years. And I'm supposed to know how they work. So actually what I'm going to be talking about today largely is what I don't know. And in particular, since right now I'm working in Greenland, I'm going to talk about whether we can predict the future behavior of ice sheets in general and Greenland in particular. And of course, I'm going to try and drive home why it matters to us, but let's see, this should work. Yeah. The background is a recent NOAA product showing the shrinking Arctic sea ice. And the sea ice, I find very interesting.
Neil?
Yes.
We have not advanced to your next slide. We're still on your first slide.
This is not good.
I know.
That is weird. It hasn't advanced.
I assume you guys advanced there.
Yeah.
We're watching a nice picture of the Earth.
Yeah, I see it as your next up, but I don't see it on the main your screen.
Oh, that's
What do you
weird.
see now, John?
Same
The first
thing.
slide, where we started.
Okay, so I didn't advance. So yeah,
Okay,
yeah, that's
we're gonna start over again.
Thank you.
You don't need the intro again.
No, Mike sure is
oh,
off.
I liked the intro. I would
You know what? I'm gonna just restart PowerPoint.
do anything you want because
Okay, so what window?
we have almost
Just this one. This is just Zoom. So that's all.
Okay.
That's open.
Yep.
Okay, this is your slideshow, right?
Yep.
Goodness me. Okay. He is the
Yeah.
host. Yeah.
Don't you want to click that one?
Yeah, sorry. Yeah.
Okay, I got first slide with writing below it.
But why did he? Oh,
Now, what
okay.
have you got, John?
First slide with writing below it.
First slide was writing below it.
Do you have the second one now?
Nope.
Nope, it's not advancing. What is going on?
Display settings, hang on.
No. It's
Let's just try it. I mean, what the heck? What do you see now, John?
I just advanced. I now see the Iceland and the North Pole.
but
And you're not gonna, your notes are toast.
I know my notes.
Trust me, he knows more than we do. He can handle it.
Yeah, I'm sure, no problem. I did, so. You want to
Yeah.
start, can we start here again?
Sure, that's fine.
Okay.
We'll see how it goes.
I'm gonna hide this. Okay. Okay, sorry about that.
Okay. So actually, this is going to be a little bit difficult because I don't normally give slideshows like this. I normally talk about deeply scientific stuff. So I'm going to have to add a little bit huge amount, but that's okay. We'll see how we get. Anyways, what hopefully you're seeing back there is the Arctic sea ice decreasing by close to 50% over the last 30 years. The reason that sea ice is interesting is because we hear a lot about climate change. Most of the data that goes into climate change is actually proxy data. It's not direct measurements of temperature. And one of the few things that really is a good over aerial view of how the temperature is changing in the Arctic and the Antarctic is the area of sea ice, because it responds very quickly with no hysteresis to the climate. So anyways, this is just really an introduction to just remind you that the climate is warming. And see, how do I go on though? Let's see. The forward button. No. Good. Okay. Of course, the climate warming is affecting the ice sheets. Here we are fairly near the margin of the Greenland ice sheet. And in summer, the early part of summer, we installed various instruments, and they were installed flush to the surface. And then when we came back in August, you can see that guy is not a midget. You can see there's about 10 or 12 feet of melt, okay? But before you get too excited, this is the sort of stuff that is reported in the media, but this is not climate change. Every year for the last 10,000 years, there's been this much melt going on. And there has to be that much melt to get rid of all the snow that falls in winter further up on the glacier. So, and just to remind you of a couple of other things, really, this is just sort of background to get you familiar with what I'm talking about. The ice sheets are big. This is a nice base map of Greenland, and it's about quarter the size of the US. So it's a big chunk of land, okay? Most of it is very high. Most of it is up around 14,000 feet. It snows, it's cold. The snow that falls is about minus 25 degrees. The only place that it really melts is a bathtub ring around the outside, down at the low elevations. And so when you hear the media saying it's melting like crazy, you have to take that with a grain of salt. Most of those people are just looking at the margins that have been melting for a long time. And I want to talk more about that. It's not that the media is wrong, Greenland is melting, but most of the stuff that they show you is the wrong stuff to show you. So let's get into what I really want to talk about. The concern about melting ice sheets is basically sea level rise. And of course, you know most of this stuff, but I'm just reminding you of it. 10% of the world's population lives within 20, 30 feet of the ocean elevation, and 7% lives within 6 feet of sea level, which means there's a significant amount of sea level rise is really a true population catastrophe. And then probably you already know this, but the 4 big sources of sea level rise. Antarctica, if it melts, 200 feet of sea level rise. However, most of Antarctica is fairly stable. And I'll mention that there's one part that's unstable. Greenland, if all of Greenland melts, 20 feet sea level rise. Mountain glaciers, 2 feet if they all melt. It's quite a lot of them. And then the other big one is thermal expansion of the ocean. And that can cause a considerable amount of sea level rise, but nothing compared with the glaciers. Right now, for the last 10, 15 years, sea level rise is being driven by mountain glacier melt. Even though it's the smallest component, turns out, and you know that from the glaciers in the Wind Rivers are disappearing. That's where most of the sea level rises come from. Right about now, I can't tell whether it was last year or it'll be next year, that'll flip and Greenland will start contributing most of the sea level rise. The big elephant in the room is Antarctica, and I'm not going to go into detail on that. What I find very interesting, though, is that 3 studies that came out in the last couple of months claim to be able to predict sea level rise. NASA, which is a reputable outfit, claims that you're going to get 1 foot by 2050 and approximately 77 feet by 21. Okay, international IPCC, international, oh God, what is it? International Panel on Climate Change. Sorry, if I had my notes, I'd be able to tell you these things. They claim half a foot next century. And then just this month, a major scientific journal came out claiming that 3% of Greenland is going to melt and you're going to get 1 to 3 feet of sea level rise. What's the big deal? I mean, there's almost an order of magnitude difference there. How come scientists don't know what they're talking about? Okay, and that's really what I want to talk about today is what's the difficulty? This is even assuming that we can predict climate change, which is another major question. But even if we assume that we know what we're talking about there, it turns out to be very difficult to predict what's going to happen to glaciers. One of the problems is that glaciers, ice sheets are very big. They're very expensive to work on. And because of that, and for other reasons, because you can get really good aerial views of things, most of the work that's done on ice sheets is done by remote sensing, looking at satellite imagery, flying aircraft over them with radar and things like that. Probably 95% of the work that's done on glaciers is done with the remote sensing. And we get some really good data out of that. However, the data that we get is basically images of what's happening now, and you can draw trend lines through that. And that's basically how a lot of the predictions for the future is done, by drawing trend lines. However, the problem is that the processes that really control the melt, by the way, I'm not going to explain the stuff over there. That's way come. That's just cadged from a NOAA site. The problem with the trend lines is it says that everything's going to happen in the future the way it has in the past. Unfortunately, we know enough to know that ice sheets are highly nonlinear. What that means is that they can go along perfectly smoothly and then suddenly jump to a new state. And so what this talk is going to try and do is talk about 2 big problems that glaciologists have very little idea how to deal with, and unfortunately, they are the two big problems that really determine whether or not the glaciers melt or not, or whether the water gets into the oceans. So to do that, we actually need to do some field work. And so I'm going to be talking about some of the field work we do. But keep in mind that actually remote field work, for instance, last summer, we were the only group in Greenland doing field work. There were hundreds of scientists over there doing whatever they were doing, but we were the only group that were doing actually going out onto the ice. And most people don't realize that there's very little work done actually out there. I guess you can see the bathtub ring of melting on that, so that's kind of nice too. Okay, so I'm going to have to give you a little primer. You probably know vaguely how glaciers work, but I wanted to stress some points. You can view this picture as either a picture of Greenland on the east and Antarctica on the west, or you can think of it as being Greenland south on the left and Greenland north on the right, because there's slight differences. But let's see what goes on here. Top of the ice sheet, 14,000 feet, snow falls on it, it accumulates. The snow builds up and the weight of the snow drives ice flow that then flows off to the margins. And the ice then has two fates. One is it can flow off and dump into the oceans as icebergs, and then the Titanic can run into it. Or it can come down and the accumulation region actually in most ice sheets is much larger. The ablation region is actually a very small region where the ice is moved into a warm enough environment that you can actually start to get melt. So you get just a little rim around there of melt. One of the things to keep in mind here, though, is the flow rate of the ice is very slow. It takes about 10,000 years for the snow to get from the top out to the edges, okay? And so in a serious way, the rate of ablation and the rate of calving has to do with how fast the ice flows. It's not obvious that the speed of the ice flowing is actually directly related to how fast it can melt, okay? That's going to become a crux point. If we want it to melt faster, we have to make it flow faster. Then the other thing just to keep in mind about this is that along with the ice flowing downwards, cold is also flowing downwards. The ice that's formed up high, minus 25 degrees. So the ice sheet is basically a transport mechanism that manages to move snow from a high elevation down to a low enough elevation so you can get rid of it into the ocean or melt it and have it run off into the ocean. Okay. Now I want to focus a little bit more on the motion of the ice. Remember the snow is turning to ice. It's being compressed by the weight of the snow being added to it. And after it's got a few 200 or 300 feet thick, the snow turns into ice and it flows down and flows out. But it's cold. And what that means is that the central part of the ice sheet is actually completely cold, and the ice is frozen to its bed, and it can only move by the ice deforming. And there's a little inset up there that shows that the ice can deform, flow like molasses, but it's very cold and it moves very slowly, and about the maximum speed that you can get out of deformation is about 10 meters a year. And since it's 1,000 kilometers from the center to the edge, you work that out and it takes many thousands, many tens of thousands of years for the ice to move out to the edge. But as the ice starts to move, you actually get shear heating, you get geothermal heating, you get several other minor effects, and the basal ice starts to warm up. And once the basal ice reaches 0 degrees C, the melting point, the ice is no longer frozen to the bed and it can start to slide. And so as you get towards the margin, the sliding in the ice over the bed, over the bedrock, starts to become important. The interesting thing about that sliding to keep in mind is that whereas the ice deformation can give you a velocity of about 10 meters per year, the sliding can give you velocities well over 100 meters per year. So you can get ice from the interior and take it out into the ablation zone or onto the ice shelves. And then there's a little blurb down there. Yeah, ice deformation controls that domal shape that makes the top stick up to 14,000 feet and get cold. But the sliding is what delivers the ice to the margins. So this is just a cartoon of the base of the ice. The ice is flowing that way. The bottom of the glacier is very complicated. You've got bedrock, you've got water down there if it's sliding, you've got ground up rock, you've got rock in the ice. It's a very complicated system. So to predict the future behavior of the ice sheets, what I've tried to do is explain to you that a fundamental thing to understand is this sliding. It's by far the largest order of magnitude factor in letting the ice flow off the continent and melt, okay? For some, I only look at the top bullet. That's what I wanted to talk about right now. I'll get to the second bullet. My notes would have told me I should have introduced it further. But just look at the first bullet. Okay, so the sliding is a crux part of the melting story. Now, I've been studying glacial sliding for 40 years, published many papers on it. Textbooks have laws that I've said about how to tell how glaciers slide. And I'm now going to admit the dirty secret of glaciology, which is that we have no idea how to predict the sliding speed. And I'm serious about that. Just to give you an example, you take me to the river flowing through town. There is one, isn't there? I think I saw one. Yeah, there's one south of town. Tell me how deep it is and how steep it is, and I'll tell you how much water is flowing down there within 5%. You know, I can do that, no problem. You take me to a glacier, and I'm supposedly an internationally known expert on this. You take me to a glacier and let me measure everything that I can about it. Everything except how fast it's going. And then you ask me how fast is it going? And I can't tell you within 2 orders of magnitude whether it's going 1 meter a year or whether it's going 100 meters a year. It's very embarrassing. And I'm the expert on it, okay? Which means that, at least I don't think, maybe some bright spark has figured it out, but I don't think so. Nobody else knows. It is the crux part of modeling glacier motion. It's the crux part of modeling how fast the ice is coming off of the ice sheet. So now, do you believe the models that tell you what the glaciers are going to do in the future? No, because we can't actually, we can draw trend lines, but we don't know if they're right. And we know, I've been working on it long enough that I can tell you that the sliding process is highly nonlinear. Very small changes change the speed of sliding huge amounts. I've worked on glaciers that have actually been sliding 200 meters a day. That means you can sit on the side of the glacier and you can watch the ice move past the. You don't usually get to do that in glaciers. Anyways, okay. So that's one problem, okay? The other problem is a big problem also. And that is, you see pictures of the melt. You see the pictures, I showed you pictures of the instrumentation sticking up in the air, okay? Where does that water go? When you're right near the edge where the media goes and takes lots of pictures, you see nice lakes and things like that. Oh, actually, you got to just move on because this is the next. No, that's the wrong one. Oh, well, we'll watch it anyways. I'll hold that. I'll hold that thought about the other problem. I'll talk about it when we get to what I'm going to do now. See, this is the problem of not having notes. What I'm going to do now is we wanted to find out about sliding. We got funding. I've worked in many places trying to figure out sliding. This particular project was funded by a group of Norwegian, Swedish, Finnish companies that wanted to know about glacier sliding. And they gave us some money, fairly large amounts of money, because this is an expensive hobby, to drill many, many holes in the glacier, mile thick, to find out what's going on underneath the ice. So this is just to give you, and when you see the helicopter, you can just see the dollar bills flowing out of the helicopters in Greenland are very expensive. Okay, are we done with that? Yeah, let's move on. We use all sorts of different transport in Greenland. We're always moving vast amounts of stuff around. This is a twin otter that we rent out of Iceland. It actually turns out to be cheaper to rent the plane in Iceland, fly it across the Atlantic into Greenland than renting it from Air Greenland. Boy, those guys make money. Oh, yes, another working on the snow. A friend of mine, one of my collaborators, sent me this. I thought it was quite cute. He just took a picture of a typical workday on the ice, and then we'd work in these conditions. And then he took a picture of a minor storm. We wouldn't work in these conditions. And then he took a picture of the sort of day where you never get out your tent or you'll die. They are, as the conditions taken from the same place. We tell the students just to stay in their tents, even if they're starving. Anyhow, the project that was the helicopter flying stuff up, we were working in one of the areas where there is a lot of melt, shown by the pretty colors on the Greenland map. And we drilled several sites to the bed and instrumented both the boreholes and looked at the bed. So how do we drill? We drill using hot water. So what we have is some miserable graduate student. This is actually up in Alaska. I've also done some drilling projects up there. Just happens to be a nice graphic. What we do is we melt water. We then take the water and we put it through a high pressure pump, pressurize it up to 2000 PSI, which is reasonably high pressure. We then put it through diesel heaters, boil it. And then we put it through, in this case, it was only half a kilometer of hose. In Greenland, we use literally miles of high pressure hydraulic hose. We then drive it down into the glacier. We put a weight on the end and just let it drill its way into the ice. It allows you to very, very quickly get access to the bed, and also you end up with a nice, clean, perfectly straight hole. And of course, the professors are always the casual drillers, and the graduate students are always the miserable helpers. In Greenland, we use a much bigger drill. This is the fastest ice drill in the world. And it can drill through a mile of ice in a day. So we can literally perforate the ice sheet so that we can see what's going on inside it. Okay. Oh, you got to see this one. These are we're just making the start to the hose to the hole, sorry, because the actual drill stem is quite long, and so you have to make a hole in the ice to start it. So these guys are just going to start the hose. That's 2,000 psi, 20 gallons per minute, boiling water. And so they're just making a hole so they can put the actual drill in.
That's because it wasn't warm. If you waited for it to be warm, it would have been okay.
Yeah, they didn't wait for it to warm up. Okay. And then we just perforate the glacier. So actually, this is an Alaskan project because it's just a nicer graphic than the one I have for Greenland. The top is a satellite image of the glacier surface. The bottom is a radar image of the glacier bed. So you can see the roughness of the glacier bed. And then the yellow bars, those are a few of the holes that we've drilled. So we literally turn the glacier into Swiss cheese. The reason for doing it is that way, instead of just getting one little sample at the bed, we can actually see exactly what's going on over a large area. Plus, we instrument all those boreholes with tilt meters and other sensors to watch the ice deform. Because if you remember, one of the ways of motion was deformation. So we actually end up with a big three-dimensional mass of data, which you need graduate students to handle because there's so much of it. So we can actually watch the ice deform. We can watch it go over the bed, going up and down, and try and piece together how the whole system works. Just to illustrate the sorts of things that we see at the bed. That's a video image that's actually ice with rocks in it near the bed under a mile of ice. It's really hard to model. It's much easier to model nice clean ice, but ice with dirt in it, sliding is a real problem. And just sampling the dirt. Just some examples of the sort of stuff we look at. And just to prove that we actually get data, this is 50, I think it's 50 inclinometers in one borehole, many boreholes, watching the ice deform over time. And so that's the actual shape of the profile. And even this sort of data is quite interesting because we have no idea why at 300 meters depth there's a kink in the deformation. It shouldn't, theory says it shouldn't be there. But the real thing that we're aiming for is the basal sliding. And I'm definitely not going to explain this. Really, this is, my notes talk about this. Really, it's an illustration of where we are in trying to explain basal sliding and the fact that we're nowhere. This is just trying to model sliding over a bump on the bed. Ignore all that. There's stress and strain and various components of the stress tensor and things like that, and velocity fields. And it's primitive. And this is where we are at the current state. A real glacier bed, we just still do not know what is really driving the sliding. Why does it vary in one place 50 meters per year and another place 150 meters a year? Seemingly identical places. We're just not there yet. Okay. I've already done the dirty little secret of glacial modeling, right? Yeah, basically all predictions of melt rate in the future depend on predicting sliding. And we can't do it. So all the models that you hear, all the predictions, all those NOAA and NASA predictions are basically just guesses. Okay. So what's this other big problem that I want to talk about? If the ice slides off. Oh, is that the 10-minute warning? Okay. Oh, okay. I'm about halfway through. A little bit more. Okay. So, yeah, right. The ice can slide off and become icebergs. Okay, and that's controlled mainly by the sliding. But the other process that goes on, and in Greenland, this is actually the most important process because there isn't that much calving going on in Greenland. Most of it is melting in the bathtub ring ablation area. Low down in the ablation area, all the snow melts, gets right down to ice, and everything runs off into the ocean. But there's a big band, much larger than the easily accessible ablation area, where there is still a lot of melt going on. Back to those pictures of the melt, but we don't actually know where the water is going. And I'm just going to show you this picture because it's so beautiful. There are huge amounts of water in the marginal regions of Greenland. In this region near the margin, you can see rock just flying in a, I think this is in a helicopter. Gorgeous place, absolutely gorgeous. Huge amounts of water, but this water rapidly gets out to the ocean because this is actually just solid ice, a little bit of snow, but mostly ice. Cracked, the water drips out and goes to the ocean. But further up on the ice sheet, what you have is 100 to 300 feet of snow. Many years accumulation, that may even be 1,000 years of accumulation of snow. That's not ice and is permeable and has holes in it, and you can pour water into it, or possibly you can pour water into it. This was studied originally back in the 1950s. The military, led by a glaciologist by the name of Carl Benson, developed a nice theory of how it all works. And this is what is sort of the accepted in the literature, or was accepted up until a few years ago. And it just talks about what happens in 1 year. Either you don't get any melt or you get lots of melt. If you don't get any melt, it's dry, nothing happens. If you get lots of melt, you saturate your 1 meter of accumulation for that year, and below that, the water runs off. That was the simple idea that pervaded how people thought about this whole runoff of water off of the ice sheet. And just for good luck, I threw in this other diagram down here that shows that the water, like in the movie that I just showed, the water can get to the bed and then flow out down crevasses and things like that. However, we've been working on this aspect of glaciers for a while too. And what you see is not what was in the literature. This is the last year's snow surface, and we've put some dye on the surface, and the dye has gone through and hit last year's surface. But then you can start seeing it's continuing down into last year's surface. And then if you dig way down and you excavate the cold snow, and this snow over here is at minus 20 degrees, excavate the cold snow, what you see are these little ice pillars, and what those are little conduits, fingering conduits that have allowed the water to go through the cold snow, even though the snow is minus 25, and happily keeps going down and down and down and down and down. It doesn't stop, and it does eventually refreeze or sometimes refreezes, but it can also end up pooling at depth. We've known about this problem for a while. In fact, in 1990, 3 of us did a traverse across Greenland, not across Greenland, partway across Greenland on skis, got dropped off by helicopter and skied about 100 kilometers, drilling holes, taking samples, looking to see what this, where this melt was going. And we wrote some papers, and I'll refer back to those in a second. But basically, we knew it was an interesting problem, but we really didn't have enough data to come up with a decent answer to this question. I threw in this picture just because I love it. This is our 1990 expedition. This is our entire stuff, including food. And that's Dave Barr. You were talking about Dave Barr. That's Dave Barr. And he eats too much, so we actually ran out of food. That's the entire expedition there, okay? More modern, okay? That's 1/3 of our helicopter load for a later traverse with snow machines and things like that, just to give you a real change in emphasis. But we got more data out of the big truck than we did out of the first one. Okay, so we went back to look in more detail, and to get down 300 feet or more, manually drilling, you're not going to get there. So we took a smaller version of the drill out, and we punched a bunch more holes at a couple of locations. And again, you have the graduate students slaving away, and I'm probably one of the people over by the drill. It's actually really cold out there because the wind just howls by you and you freeze to death. But and this is just something to watch while I talk. We also did some traverses with snow machines, stopping, drilling 100 or 200 meter holes, and getting ice cores out so we can see what's going on below us. And this is just, so you can see what it's like to work out in Greenland. And there's a core barrel. Oh yeah, they're going to lower a core barrel down, and then they're going to put extensions on. Lots of extensions. Keep going, guys. Lots of extensions. It's a long way down. And eventually, they'll take an electric drill, big, huge electric drill, and drill, and then pull the whole thing back out again. Come on, guys. They work hard. Actually, I'm one of those guys. Anyways, and you get a little piece of core, and you keep going. Then what you do is you put instrumentation down the hole. So you can, what we found is the best instrumentation in this situation are temperature sensors, because you can actually see the water with temperature sensors, because the snow is -25. Anytime there's any amount of water, the phase change energy warms up the snow, and so you can actually track the water with the snow. Yeah, I'll let this one run just a little bit. This is our camp, and the reason I wanted you to show it to you is just to make you realize how big Greenland is. You can't see anything. You are on an infinite flat plane. You are in the middle of absolutely nowhere. In some ways, it's the most intrinsically boring place in the world. Nothing is happening. We had a drone up there, so we were getting these pictures. You don't see anything in any direction. Well, except Clement is running one of our French students is running the drone. Okay, this is really just to prove that we did something. We did a traverse with 12 sites. We drilled 12 of those holes, and we obtained a bunch of data. And just to show you that it really is non-obvious what we found, and this came as a bit of a shock to a lot of glaciologists. is here you are in the middle of Greenland. Well, it's not the middle, it's near the, it's not in the ablation area, but it's not in the center. And it's cold, minus 20 degrees snow here. 14 meters down, there's an aquifer. There is liquid water. Okay, it's being stored. If it's being stored, it's not flowing into the ocean. And that's the big kicker. The way I thought you might be interested in this is the way we traverse. We take a snow machine, hook up people behind it, put a survival bag on the snow machine in case it breaks down, and head off across the ice sheet. And of course, the professor gets to drive the snow machine. Actually, driving the snow machine is the most dangerous thing, because if you go into a crevasse, you're the one that goes in. You have to hope that these guys pull you out. Just like, how do I end that? There we're about 6,000 feet. We're heading back to camp, which is about 10 miles somewhere off in the distance. Yeah. Oh God. Yeah. This is the old picture on the top, okay? But the crux, forget about all this garbage. The crux idea is that little thin blue line, that's last year's snow. So that's the top diagram. And what we've discovered is that there is a huge amount of stuff going on below it. And what's really going on below it is we're storing water, storing huge amounts of water.
So which part of it slots? Just the top layer?
No, the whole thing. No, the whole thing slides. This is a separate story from the sliding. I've confused you by telling two stories. The first half of the talk was about sliding and the whole glacier from top all the way down to the bed. Okay, that whole thing slides. It also deforms while it's sliding. So a mile deep ice slides at 100 meters a year towards the ocean. The fracture, which one?
Where it says max depth of water.
Oh, okay. Okay, so the ice is 1 mile deep and it's ice, okay? And ice is impermeable. Water can't go through it, okay? But the top 300 feet is snow, and snow has holes. Now it gets compressed by the overlying weight, but it has holes in it, which means that if you melt the surface, then the water can go into the holes, okay? So this is a whole different problem. Well, this scale here is 100 meters, whereas that scale up there is 1 meter. And that's what we really discovered, is that you can't just look at the top layer of snow. Really, you could just stand back and say, all we discovered was that we need to look at the top 100 meters of snow. Okay, you could look at it that way. I always like to look on the negative side to make you realize that you just spent $1 million to discover nothing. Yes. Oh,
The highest point.
yes.
In Greenland, top of the ice sheet. You've got about a mile of ice.
Actually, it's more than a mile. You've got actually close to 2 miles.
So the bedrock underneath it is up around 89,000.
No, see, that's why the bedrock underneath is basically sea level.
You got 14,000 feet.
You
of
got
ice.
14,000 feet of ice.
Oh,
Okay. So actually that brings up a really good point, which is when you see the media saying it's melting like crazy, about the fastest it can melt is a foot or two a year. Okay. So Greenland's not going anywhere. I mean, it may be melting like crazy, but if you're melting at 2 feet a year and you got 14,000 feet to go, you know, it's not, in 10,000 years, there's still going to be some ice there. Okay. But this is a different thing we're talking about here. This is just pointing out that there is a huge amount of water stored in the in the snow. And what that means is that you're buffered against, basically climate change is buffered. You can melt the surface like crazy, but the water just goes into the snow. Now, I'm going to gloss over this just because you can ask me questions about it, but basically it turns out it is even more subtle than that. It turns out that people have sort of known that there's a possibility of water going into the snow, and people have thought about that. And unfortunately, this black line, this is the line that we produced when we skied across Greenland on skis, and it turns out it's wrong. What it tells you is that if you're in the region above the black line, in theory, you can store water. That's the temperature of the snow and the density of the snow. And so just to make it that understandable, no, I'll just say one more thing. We've developed a new theory, and it seems to work. We have 2 data points. Those data points cost a lot of money. The little blue dots in our theory is the red curve, and it fortunately goes through the blue dots. Let me explain what this actually says, because it's not obvious. What it says is, let's say you have snow at a density of 700 kilograms per cubic meter. That's fairly dense snow, okay? You can pour water into it because there is lots of pore space. The pore space closes off at about 825. So you can pour in about 20% of the volume of that snow. You can fill it up with water because there's 20% holes in it. What that means is that if you've got 100 meters of snow like that, you can pour in 20 meters of water. Well, that's 100 years of melt. What that means is that you can turn up the climate for 100 years, nothing happens because the water just goes in, okay? However, the new model says that if you have 700 density snow, you can only pour in just a little bit before it seals off. And I'm not going to go into the theory of that, but it's a neat new result that was just published and is causing considerable confusion. But bottom line is that the snow is basically a sponge and can store a huge amount of water and buffer the climate change. And this work is actually making reasonable progress at finding out just how much it can buffer. Okay, so we're actually making progress on this one. So, oh, good. What I've tried to do is show you that future sea level is going to be really, really hard to predict because the big players are the ice sheets. And we don't know the crux mechanisms. And this is not something that most people will admit. So the good news is that we actually are making really good progress on modeling this buffering in the snowpack and where the runoff occurs. And the current project that we're working on in Greenland, we've got some really great data from this summer. We put in the 14 sets of instruments just before COVID hit in the accumulation area where the snow is building up. And we put 10-foot poles on them to make sure that we could find them again. And then COVID hit. And so we weren't allowed to go back. And so we lost them all. But we actually found one site that had great data when we went back this summer. So we're really happy about that. It actually it's helped really define this problem. But the real bad news is this sliding problem that I've tried to explain to you, that we just don't have a good handle on it. And it's embarrassing because I've been working on it for my entire life. We're not making very much progress on it. And unfortunately, the modeling community doesn't really accept the fact that the models that are in the textbooks, when you actually take them into the field and try and apply them, don't actually work. So that's my talk. And apparently I can now ask for questions at this point, right?
Can you make any generalizations about how much of the summer melt goes into the ocean versus goes into the ice?
Depends where you are on the ice.
Can I stop you for a minute? Please,
Yep.
please repeat the question.
What percentage of the summer melt goes into the snow compared with what goes into the ocean? That's what you asked, wasn't it? Yeah. Depends on where you are on the ice sheet. When you're near the margin, most of it runs off into the ocean. As you go further up on the ice sheet, more and more goes into the snow. And eventually, when you get about 100 kilometers, 150 kilometers in from the margin, all the melt is currently just going into the snow. So, and it turns out it's a big number.
Melt then refreeze as it gets buried by newer snow?
No, yeah, no.
Please repeat the question again.
That's, oh, all right.
This is Big Brother. Repeat the question.
Yes, yes, I am chastised. Does the water that infiltrates into the snow refreeze or what? And it turns out that that is a very interesting story. When you're really high up on the ice sheet, the water infiltrates, yes, and it does refreeze. And that's where you see those little ice pipes that I showed you pictures of. But further down, the amount of water, the amount of melt that's going in, because it bypasses all the cold snow, which means all this cold that could refreeze it, doesn't refreeze it. And it stops at a certain point. And I didn't want to do this picture on the left, but we actually wanted to investigate just exactly that question, okay? So what we did is we drilled a 100-meter deep hole through the snow. And then we poured water in. Actually, I lied. We drilled the hole with water. But in effect, we pumped a whole bunch of water into the snow to see where it went and what happened to it. And this is a diagram of the temperature in the snow over a week. Okay, we put a whole bunch of sensors down the hole. We always love sticking sensors down holes. And what we see, these are one day apart. And what you see is that in some places, the snow cools really quickly. Down below 45 meters, it cools really. What that means is that the water didn't go into the snow. If the water had gone into the snow, the phase change to freeze the water would have released a bunch of heat. And so you can actually track where the water is. If there's lots of water, it releases a bunch of heat when it freezes, takes the cold content and warms up. So this cooled down really quickly. No water went below about 45 meters. Above it, a fair bit of water went into the snow. It was nice and permeable, but it cooled down. But at 45 meters depth, even after a week, it hadn't refrozen. What that meant is that there was a lens of free water down there. And the picture I showed you of this, that water has been there for over a year, okay, and it hasn't refrozen. And since we discovered this, people have been clued into this. And so they've started looking at radar imagery, and what they've discovered is that there is a bathtub ring around Greenland of buried water in the snow, which is filling up with climate change. Okay, so there is actually, 30 feet beneath your feet here, you're driving your snow machine over it, is basically a lake, but it's a lake that extends for miles and miles and miles in every direction.
So why doesn't that lake freeze?
Why it doesn't freeze, one of the things that, water is strange stuff. Water has a huge phase change energy. The amount of energy that you have to take out of water to change it from 0 degrees to ice at 0 degrees, not change its temperature, is the same amount of energy that it takes to almost boil the water. Okay, it's a huge amount of energy. So if you have some water and you want to freeze it with cold snow, okay, you have to take the heat out of the water and put it into the snow. But you can heat up just to freeze 1 cube of water. You have to heat up 160 cubes of snow, okay, 1 degree. So it requires a huge amount of cold to freeze water. It's really quite spectacular. So that's why this diagram is so important. What it's showing you is that that pooled water is taking a long time to freeze, even though that's all that is like 3 drums of water. It's not a vast amount of water, but it's taking a week for it to freeze, even though it's just a layer like this, and it's got minus 25 degree snow below it and minus 25 degree snow above it. It's taking a week to freeze. We're finding aquifers that are 20, 30 meters deep, thick, buried deeply in this snow. That's where the melt, the climate change melt is going right now.
And then that liquid water, is that stable?
He asked whether the liquid water is stable. It depends on the location. The ice sheet has a very, very gentle slope because it is, fractions of a degree. Okay. But we have found in a couple of places where it's actually flowing very slowly down the glacier gradient, and it actually crops out at the surface. You ever heard of pingos? There are strange features in northern Canada and Alaska where the ice erupts in the surface of the tundra. Anyways, we've found pingo-like structures down low in the accumulation area where the water has actually come out to the surface and then refrozen when it gets to the cold air. Strange features that actually sort of prove. Don't forget, all this is going on below where we can see. So it's all reconstructed from data. So it's kind of nice that when you see it popping out somewhere, when you see the water popping, whoa, we actually predicted the water should pop out, and it did. You like to be convinced of your own. Yes.
Is what's happening in Antarctica generally similar to what you're describing here, or is it a totally different phenomenon?
Is what's happening in Antarctica similar to what's happening in Greenland? Yes and no. The storage of water in the firn, no. And the reason for that is Antarctica is colder, and so there's very, very little melt. Percentage-wise, in Greenland, there's not that much icebergs, there's lots of melt, okay? In Antarctica, it's mostly icebergs, not much melt. So that part of the story is not very important. What is important in Antarctica is sliding, hugely important. And I don't know, just today there was a big news feed, something about like the Voodoo Glacier or something like that. There is a part of Antarctica called West Antarctica that is below sea level. The base is, but you asked me about the thickness of the ice in Greenland. In Antarctica, there are parts where the bedrock is actually below sea level. So the only reason that the water isn't there is the weight of the ice is keeping the water out because the ice is so thick. There's a place in West Antarctica called the Thwaites Glacier, which is bedded quite a bit below sea level. And if it starts to slide faster, it will actually allow the seawater in underneath and float the entire glacier. And if that happens, we could see 3 or 4 feet of sea level rise on a 10-year time scale. Okay, that actually, as far as glaciologists are concerned, that particular glacier is probably the most worrying one. Yes.
Is this what you were referring to as nonlinear behavior?
Yes, there are many nonlinear behaviors in ice sheet behavior. And one of the big ones is if you have the ice grounded below sea level, okay? If it's nice and thick, then it pushes down on the bedrock and keeps the ocean out. But if you start melting it and it gets thinner and thinner, it's pushing less and less, and ice floats. So if it gets thin enough, it'll start to float. And once it starts to float, it's gone. There's a huge part of the Antarctic Peninsula called the Larsen B ice sheet. And that's what happened to it. It basically just floated away. And though that's a completely nonlinear behavior, because it will behave on a nice little trend line, and then turns into icebergs and ice cubes and floats away, and it's gone. So, yeah.
Zoom questions.
Oh, Zoom questions? How do I, oh,
So far, I've not seen that we've gotten any Zoom questions.
oh, that means my explanations were so clear.
Absolutely perfect.
So how much does it actually snow, 25 below at the summit of the Greenland ice sheet? And can you talk about how old is the Greenland ice sheet?
Okay, the question is, how much does it snow, especially in the central part of the ice sheet, and how old is it? I'll answer the first one, the first question, because it's quite interesting. The central part of the ice sheet in Greenland is part of a major weather system. And so actually it does get a certain amount of snow, several inches of water equivalent per year. But it is high enough that you're starting to get into what's called an altitudinal desert situation. And I'll switch to Antarctica. The central part of Antarctica really is an altitudinal desert where they get that much snow a year. So there's hardly any accumulation. But Antarctica is so huge and it's so flat that it still builds up. But so, yeah, Greenland is interesting because it is part of the climate, the northern hemisphere climate system, whereas Antarctica is in its own polar vortex that doesn't interact with most of the rest of the world. So it gets less accumulation. How old is it? That's actually a discussion. Whether or not it survived the last interglacial, which means, did it survive 120,000 years ago? And there's an argument on that. Most people are on the side of it. Yes, it survived. It probably reduced to about 1/3 of its size and then grew back again. Okay, but unfortunately, all that evidence is buried underneath the ice. So it's hard to get to. Antarctica has been there for 4 or 5 million years, although parts of it have broken up.
So when do you think it started, though? The ice started, it was too late.
Oh, you got to remember that in geologic
Repeat the
terms.
question.
Oh, sorry. When did the ice sheet start? In geologic times, we've had 4 or 5 major glacial periods, including snowball Earth, 500 and some odd million years ago. The latest ice age started, and again, it's fairly variable, 5 million, 4 million years ago, um, related to several events, one of which is the closing of the Panama Isthmus of Panama, stopping the connection of the big oceans. Greenland has been there for, or ice has been in Greenland for at least 2 million years. Antarctica somewhat longer. Again, the problem with Greenland, however, is that most of the evidence for the glaciations are actually under the ice, so you can't get to them. So I can't give you a precise date on that one. Yeah.
Just a comment. The amount of ice that's been lost in Greenland has accelerated quite a bit. And I guess in the last 30 years, it's 6 times more than it had been. Does your analysis or the recent data suggest that that any projections on this that we're going to be storing more water and we won't have quite such an issue going forward, or?
First off, yeah, I'm trying to rephrase the question. You stated that the amount of
loss of ice is probably in the last 30 years 6 times the rate. It's gone up
okay.
6 times the rate.
The
Projections, I guess, looking forward from
here. Yeah, the question is the rate has gone up by 6 times, and I have to question because actually that's based on some proxy data which may or may not be correct. It has gone up. I just I hadn't actually heard the 6 times before. It seems more than I've heard, but it doesn't really matter what number it is that you're saying. Yes, Greenland is melting more. What I'm trying to point out is that predicting is really hard. There's a couple of things that are going on in Greenland that makes it even harder. For instance, your 6 times, that a lot of that may be related to Jakobshavn ice spray, which is a huge fjord, which is draining a large part of the ice sheet, which about 20 years ago really started speeding up, and it's been draining into the ocean. Okay. And that's the largest increase that I know of. Helmheim on the other side has also been doing it a bit, but Jakobshavn is truly impressive, the amount of ice that is coming out of there. That's another one of these nonlinear things. Turns out that as the climate warms, oh God, this gets complicated. The whole coast of Greenland is a series of fjords marching up the coast. And as the climate warms, the locus of fast sliding actually moves north and goes into the next fjord up. And so you get a whole section of the Greenland ice sheet draining quickly in a nonlinear way until that area gets drained, and then it slows down. And then when the climate warms, it eventually moves up to the next major fjord system, and that area drains. It's almost like draining a drainage basin of water. You're draining different regions of it, but it's not a simple, again, going back to the trend line, Alan, just because it's increased, and I'll take your number 6 times in the last 30 years or whatever it is, that trend line, there's no guarantee when it's going to stop. I'll give you a good example of that that's maybe a little bit easier to understand. Another one of my drilling projects, we drilled through the Columbia Glacier, which is near Valdez in Alaska. Okay. We drilled through it. Now it's open water because in 1970, the ice started retreating. It then started retreating really quickly. It dumped icebergs. The Exxon Valdez tried to avoid one and ran aground and spilled oil. It dumped a huge amount of ice. It is now doing nothing. because it drained that fjord. All that ice went out into the ocean. It got back to the mountains and stopped. That's why I'm having a hard job answering your question, because
Suggesting a lot of the issues are these non-linear effects.
yes, yeah,
That's why it's hard also to predict what is going to happen.
yes,
In 30 or 40 years, because catastrophically, some of these things get
yes. And you would just, I'll just reiterate, you're just restating that the nonlinear effects can have dramatic results. And that's one of the reasons, going right back to the beginning of the talk, when I pointed out that 3 very reputable groups of glaciologists have predicted, not that far into the future, completely different answers.
Well, I know the IPCC report, you mentioned it, something like a foot of seawater.
Yeah, half a foot,
Half a
yeah.
foot. But big caveat, there's a big caveat in that report, which is these non-linear effects.
Yep.
And if they take off, it could be a lot more than that.
Yes, yeah.
So Neil, we did pick up some questions from Zoom, if I may.
Sure.
The first one is, does the hot water drilling technique influence your measurements of the temperature of the ice? And how does the temperature of the ice drilling differ at depth?
Good question. And interestingly enough, I wrote a paper on that. It was my first really big successful paper, because we drilled a hole in Antarctica. And in Antarctica, this was early on in the days, and we had problems. The hole only lasted for a couple of days, so our instrumentation died. And so I had to figure out how you, with just a few temperature measurements in a fairly warm borehole, how you would possibly figure out what the actual temperature was. So I actually wrote what I've always thought was a really nice paper on that. It turns out that you can model that quite. Heat flow is really nice. One of the reasons that I do a lot with temperature is that heat flow is easy to model. And so you can do fancy things with it. So yes, we can figure out what the temperature is. Yes, it does greatly disturb the temperature field. And where is it? Oh, and actually this left picture is a good example of that. If you wait for a week, the temperature gets close and you come back next year. By the way, we leave data loggers in place for years, collecting data, so we can come back the next year and get the blue line, which is the decayed temperature. And that really is the temperature of the ice.
So in looking at that figure you have up there, it actually, the borehole is kind of the dotted line and you've injected the water, or is it the flip side?
This is just a temperature plot.
Okay.
Okay, that's all it is, a temperature plot. So we drill the hole with hot water. We instantly put down a hole. I think we put down 100 temperature sensors down this hole. Okay. And we immediately read the temperature in the hole. And in fact, we read it so quickly that the water down at the bottom is still at 5 degrees plus. So it's still hot from hot water drilling. The next day we come back. All right, so the data logger is collecting data. I just select next day's data. And that's the temperature, messy. A few days later, it's cooled. And eventually, when we leave it a week, it's almost to what the background temperature is. And we assume that when we come back next year, that all the, actually you can do the calculation, all the heat is gone next year.
So the blue is the background, pretty much the
Blue is the
background temperature?
background temperature,
Yeah.
yes.
Okay.
Yeah.
Had a second question. Seems like the water storage associated with melt has the potential to result in catastrophic sea level rise over relative short periods of time when it reaches some tipping point. In other words, this is your Antarctic example. Where,
Yes.
yes.
But the answer, I think, and this is just off the top of my head, is the answer is no. because I don't see a tipping point in it. Basically, it's a situation where you fill it up, and once you fill it up, it starts to overflow. So there's some non-linearity there, but it's not, I can't see any reason why it all of a sudden drains out just because it's being filled. I just think you start getting more runoff at that point. But that's my gut feeling. You might be right.
Okay. So as you think about the things you worry the most about affecting sea level rise, it sounded like this one in Antarctica where you get the water underneath the ice and where you can, you talked about 3 feet in 10 years kind of change.
Yep.
In Greenland, you talked about the slip of the ice, and you also talked about the water within the ice. How do you, what of those do you worry the most about causing catastrophic, fairly rapid sea level change?
Okay. Good question. The glacier in Antarctica is the one to worry about, but the problem is we've known about that glacier for a long time, and it's been questionable for hundreds of years. So yes, it could start breaking up next week, okay? But actually, there's no reason to expect it to break up next week as opposed to next century. So of all the things out there that could cause catastrophic sea level rise, it's one of the big ones. But I don't see it, it's not something I lay awake at night worrying about. There are other ones around the world. There is a volcano underneath northern Greenland, which is causing the ice to slide very rapidly in the northeast ice stream. Volcanoes are very unpredictable. If that erupts and starts dumping huge amounts of heat, we could see sort of the northeast chunk of Greenland slide off. There's lots of things out there to worry about. If you want me to, I can keep going, but I think I will stop.
On that note,
Let me just make one comment, Mike, for a quick second. So tell me that I'm wrong, I hope, but what I've concluded from this is your ability to predict sea level rise is about how good my ability as a geophysicist is to predict the next earthquake.
Yes. Considering that I actually worked in the Caltech earthquake prediction lab for a year, I fully appreciate the difficulties of that. And there is some possibility of predicting earthquakes. And they're about the same as, predicting sea level rise. So
Wow.
I totally agree.
Ouch. Oh, it's all yours, Mike.
so Neil, we want to give you a small token of our appreciation for making the trip out here and giving a wonderful presentation. The drill with the chairs is the usual, half this way, half that way. October 4th, Geological Survey geologist, Dr. Mauk will be here, and it will also be an excellent presentation. Please join me in thanking Neil for an excellent presentation.